And just coincidentally, on another project, we were imaging lung, looking for a two-photon process to detect elastin, which you can see in this lower left picture. And we saw these little flecks of what looked like melanin in the alveoli of the lung. We went to CW excitation. Everything disappeared except for those flecks. So we believe that there's actually melanin there in the lung. Another thing that we've learned about this process is that we know that photobleaching is a problem in fluorescence, and we know that oxygen is involved in the process. If we do our experiments in a nitrogen environment, instead of having milliseconds, tens of milliseconds of lifetime, this is in the vertical direction is time, the horizontal direction is position, and there's 1 grain of melanin, we can extend the fluorescence to last for a minute or more. That allows us to do experiments like this middle panel where we look at the power dependence, the excitation power dependence of the emission. And we see that for the blue excitation we have a linear dependence, which is traditional for fluorescence. For the infrared excitation we have not a second order fit, which we thought for a 2-photon process, but a third order fit indicating that it's a 3-photon process. And once again, I just reproduced this picture here so that you can see where those are occurring. Okay, conclusions. With infrared excitation, we can enhance the fluorescence by a factor of about 1,000. It's a stepwise there is a stepwise 3-photon excitation process in addition to the single photon process. Photobleaching is reduced in the nitrogen atmosphere. It's also reduced in the hair where the melanin is enclosed in the hair, and oxygen is less accessible. The 2 emission components, at least, the linear and the third harmonic. We've imaged these so far in hair and in lung. And we also detect the near-IR fluorescence in addition to the visible fluorescence, but it is indeed much weaker. The real significance of this work for the present talk is that this technology could, because it's a CW laser, this technology could easily be retrofitted onto a conventional confocal microscope with the addition of 3 components. A beam splitter to split off the visible light, a filter to remove the infrared, and an additional detector. Thank you.
Very quickly, we're going to go through just some of the steps that Lucid has taken to succeed in this marketplace, and then we'll talk a little bit about some of the challenges that we face. As everyone in the room is aware, without capital investment, things don't move along very well. Certainly you guys have challenges to receive grant and funding for the research. Lucid also has challenges in securing private equity, or private investment rather, to help us really get this thing commercialized and rolled out into the private practice, which is where we think that Confocal can make a tremendous difference in the lives of patients. The FDA, we've actually had pretty good luck with the FDA. I think much of it is in part or due to the excellent collaboration that we share with Memorial and Northeastern. Our initial FDA clearance was a 513G, and we had 0 efficacy data, and we were able to get an intended use statement that allowed us to sell the Vivascope as a medical device without having any efficacy data. We did that by simply adding a contraindication that said, we're not going to use this as a primary means of diagnosis. This is going to be an adjunct tool. And that really led the way for many clinical studies to be done. Some of the papers that Milind referenced were done under that contraindication. Today, I guess, let's see, back in 2008 we went through our 510K process with the FDA. It took us about 8 months, and we received a new intended use statement from the FDA that now does allow confocal images to be used as a primary means of diagnosis, so that the physician can use confocal images alone and render a diagnosis based on those images. Clinical trials, we've had very good luck with our clinical trials. Lucid is a small company. We don't have a ton of money to dedicate to clinical trials. most of the work that has been done has really been done at arm's length from Lucid. Researchers have bought their device, designed their own trials, got the necessary ethics approvals on their own with very little financial support from Lucid. In most cases, most of what we can do is offer a bit of a discount on the list price. And today we have more than 250 peer-reviewed publications in the scientific journals. One of the things that we learned early on was that confocal images are great by themselves, but it's even better when you can collaborate. And so what we've done is we've integrated with information technology and created something that we call VivaNet. VivaNet is really a way for us to transmit the images that are done at a clinic someplace, and we can send them to a remote dermatopathologist for interpretation. This allows us to collaborate in near real time, allows more facilities to be involved in the clinical trials, and really results in much better work. Some of the most noted work has been done between Modena, Italy, and our friends in the Sydney Melanoma Institute using a VivaNet-like system. Education and training to date, Lucid has sponsored much of the education and training that goes on. We bring in world's experts on the interpretation, and we deliver courses, or they deliver courses rather, to teach how to interpret. This is a little bit different than standard histopathology, so it takes a little bit of getting used to. Education and training, as Milind said, is a challenge for us, and we need to continue to develop ways to deliver that education and training faster and at lower cost. Talked a little bit about the opportunities and challenges, and certainly from Lucid's perspective, one of the biggest opportunities that we have is our business model. How do we take this confocal microscope that's a wonderfully accurate clinical tool, and from Lucid's perspective, how do we make money with it? How do we get it out into the hands of physicians, and how does Lucid stay a viable company? We think VivaNet is really the way that we're going to do that. This is the business model of VivaNet is a click model. So every time a dermatopathologist reads a confocal case and makes a diagnosis, Lucid gets paid. So the current commercial VivaNet status is that we today have 3 servers online. We've got one for commercial, real diagnosing. We have a clinical study server that allows researchers to collaborate back and forth, and then we also have a training library server that's up and running. We have 10 readers online today around the world, and we have 20 imagers. So the readers are just accepting these cases from all over the world. The imagers are stationed all over the world, and all they're doing is collecting these images with the confocal. Certainly we intend it to be used as a commercial tool, but there are some other uses for clinical studies. It's a wonderful tool. It allows real-time, up-to-the-minute recruitment data. It allows a very nice, friendly collaboration environment where multiple people can be working on the same image sets. And we can also enforce rules to blind certain researchers to certain portions of the data sets, as it relates to the study. And then the final thing is that we've learned much of this through Memorial Sloan-Kettering is that patient health information is a big deal. It's important to keep that data secure. And one of the things that we've been able to do with VivaNet is we can actually break up the identifiable patient data and store that separately from the images. And that can be stored, the identifiable patient information can be stored internally. Milind, you talked a little bit about the machine algorithms and things like that. The one piece that I just wanted to note there is there's another company, Mela, out there who has a spectroscopy device that's using this algorithm to make a diagnosis. And what we've seen is that it's been very challenging for them to get it through the FDA. I think anytime you're using an algorithm to make a decision in terms of patient care, biopsy, don't biopsy, surgery, don't surgery, we're going to have a very difficult time getting the FDA to buy into that. But I appreciate and like very much your thoughts of how we can draw the attention to a particular portion of the image based on some features that we see there, and doing that automatically will be tremendously beneficial, I think. We've been lucky enough to work with dermatopathologists who are licensed in multiple states. And so the system knows where they're licensed and sends only those images which they're licensed and credentialed to read. So it's kind of a rules-based system where we can set up these rules and only send images to the appropriate reader.
It's not a 24-hour online system.
It is a 24-hour online system. It's the rules that are being enforced. Every time the image set is captured, we know where it's coming from, we know where that patient is based, internal to the system. The system can now route that to an appropriate dermatopathologist who's licensed.
Great.
Make sense?
Yes, thank you.
Sure. Any other questions? Go ahead.
I have a question for Chuck. How do you know that you were indeed looking at melanin, and how come you got so much signal out of the 3 photons without a pulsed laser?
The question is, how did he get so much signal without using a pulsed laser?
Second question was the strength of the signal. The issue is that in a normal 3-photon process, the intermediate states are virtual states. So it's really, if you think of it quantum mechanically, it's third-order perturbation theory, so it's a very, very weak signal. In this case, you actually have real states to excite. So the first photon excites a state appropriate to its wavelength. Maybe there's a little bit of decay there, and then the second one comes in and excites the next state, and
So
then
they're more
the third one
persistent
comes in. So
states?
they're actually real states. So you have, instead of having a femtosecond to get the next photon in, you have a nanosecond. And that, if you just look at the numbers, it says 10 to the 18th improvement. It's not really that good, but you do get a great improvement. Okay, so first question again.
The first question was, you didn't show any, immunolabeling type information. So how do you know that, you made some conclusions about what you were looking at?
Okay.
I want to know how you...
Good
how
point.
you
Good
trust
point.
me.
At this point, what we have done is we've made the measurement on the purchased melanin, the squid ink, which is extremely pure melanin sample. So we know at least that is the signal of melanin. Yes, we still need to confirm that what we're seeing in the in vivo samples is really melanin, but it has the same excitation spectrum, the same wavelength spectrum, and the same stepwise characteristic. That is, we can excite it both with the CW and pulse laser. So the probability is very high, but we do indeed need to confirm that.
Okay.
Good question.